Okay, so today we will talk about the second method for solving recurrence. And a little bit recap of the previous contents. So we use the maximum sub-array problem as an example to introduce the divide and conquer approach or divide and conquer algorithms. So this type of algorithm contains a recursive part or recursion parts. So in a recursive algorithm, the running time of the original problem is described by the running time of smaller problems. So that's why we will need to use a recurrence equation or recurrences to solve the or to represent the running time. So the substitution method is the first method we talk about. Actually, it is the way to strictly prove that a solution is correct for a recurrence, okay, based on the principle of mathematical induction. But one shortage or one shortcoming of this method is that we need to have some guess about the solution in our mind, right? So maybe it could be a guess based on our previous experience. For example, we know that the merge sorts, for the merge sorts, the recurrence looks like T of n equals 2 times T of n over 2. So, and plus a constant time function. So plus some linear time function. So that sort of recurrence could be could provide some hints to other types of recurrences in similar form. But the problem is that it is not necessarily, or it is not always the case that we come across with similar recurrences. So in today's lecture, we're gonna cover recursion-tree method, which is quite an intuitive way to get some clues about what kind of the solution for a recurrence could be. We need a pen and a paper to draw trees, but I will show some animation on my slide, and I hope that is sufficient for the visualization purpose, but it always helps if you can try it on different types of examples on paper. And the master method, which I hope also to cover at least the majority part of it in the lecture today, because it provides a systematic method for solving recurrences. And some questions in the first assignment also requires that we use master method or the so-called master theorem to solve recurrences. All right, so let's get started for the recursion tree method. Okay, it is to help with the shortcoming of substitution method, because we want to have a good guess about the solution, right? So we can draw a recursion tree. Basically, we draw a recursion tree to help us devise some good guess. Actually, this is not the first time that we see a recursion tree, because when we talk about merge sorts, we already draw some tree-like structure on the slide, right? So the basic idea for this method is that when we draw a tree, we use a node to represent the cost for a single subproblem. Okay, the node starts from, we start from the highest level, which is the root node. Okay, and then we do the splits, and the nodes resulting from the split represents the cost for the corresponding subproblems. Okay, and after a tree-like structure or a recursion tree is drawn, and then we will, it is PowerPoint already available. I uploaded the PDF versions. upload the PDF to Canvas. I think you can see it. Okay. So after the tree is drawn, we will need to sum the costs within each level to get a set of per level costs. Okay, so we basically count or calculate the sum for each row for each level in the tree. And we sum up all the per level cost to determine the total cost, because we use the node to represent the cost for each subproblem, and the solution to the original problem consists of the solutions to all the subproblems. That's why we need to sum up all the nodes. Okay, so let's use an example to show how this method works. Okay, so this time we're not going to use the same example for merge sort or maximum sub-array problem. And we're going to use some not that regular kind of recurrences. So the recurrences says T of n equals 3 times T of n over 4 to the floor plus some quadratic function described by big theta notation. And we would like to know the upper bound of T of n, which is you can describe by big O notation. Okay, so just some tolerance on the sloppiness, so we can basically ignore the floors or ceilings. Okay, and for a quadratic function described by big theta of n square, we can use c times n square, and c is some constant. Okay, so with this recurrence rewritten like here, and we are able to draw a node starting from the root node. Okay, so that is we can first write the original solution here, because T of n equals the c times n square plus 3 times n 3 times T of n over 4. So we put the function here as the root node. Okay, and that is the cost, basically describes the cost of splitting into subproblems and combining the solutions from the subproblems. And we put the cost for solving each subproblem as children nodes for this first. We call this level 0. This is our level 0, and this is our level 1. So we put the root node as level 0 and all the subproblems into level 1. That is our first step of the split. And we can further split the subproblems, as we can see here. So how do we get this? The c times n over 4 to the power of 2. So that is simply to substitute n over 4 into this original solution, into this original recurrence. So if we let n over 4 to be the n in here, then what's here would be T of n over 4, right? So that is n over 16. And also there's a 3 here, and plus c times n over 4. Okay, so we do the substitution, and that means we can obtain the further split. Okay, we got T of n over 16. So that is a even smaller subproblems. Okay, so hopefully this shows the idea of drawing the tree, because we can further split the subproblems into a deeper levels. Okay, so but just the the part 1 is there. Oh, really? So let me quickly upload it. I think it's quite convenient. I understand that the slides are helpful in keep up with the lectures. So I will upload a new file here. With this divide and conquer full algorithm. Yes, I think I find it. Open and add item. It's uploading and it's published. Yeah, I think if you refresh the page on Canvas, and you'll be able to see it. It's with the name Lecture 4 Divide and Conquer. Alrighty, so let's continue with our recursion tree here. All right, so I think we will realize an issue that we don't know when the split should end, right? But eventually it will end because the problem cannot be splitted infinitely. It will always hit some point where it is the smallest case for the problem, right? So if we continue spending, we would eventually hit some points that the split stops. And that means we reach the leaf nodes. And a leaf node in the tree means that this is the smallest node, and it cannot no longer be splitted. All right, so before we reach that part, let's first look at the properties of the tree, the resulting trees. And because the principle is to look at per level, look at the per level summation for the tree, right? And if this is the level 0, right, the summation is c times n squared. And if we look at the second level in the dash line blue rectangle here, we call it level 1. And we have 3 of such nodes, and each node is c times n over 4 to the square. So that is 3 over 16 times c times n squared. That is the summation for the level 1. Okay, and we simply look at level 2. It is 3. It is there are 9 nodes, which is 9 squared, 9 to the power of 2, or 3 to the power of 2, which is 9, right? And each node is c times n over 16. So in total, the summation of the level 2 is in this form, right? And a little bit comparison with the previous node, right? Right. The coefficient here is 1, and here is 3 over 16, and here it is 3 over 16 to the power of 2. So now we may guess that, okay, it could be a pattern here. And maybe for level 3, the total summation is 3 over 16 to the power of 3, right? So it gives us some hope to solve this per level summation. And then after we know the per level summation, we're going to sum up all the nodes, and then we would like to see that something like a geometric series. And the geometric series can be calculated. The summation of a geometric series can be calculated, and that is something we are looking for. So in the next few slides, we're going to further check whether this is the case, to see if this is the geometrical case. Okay, so we want to know the general expression for level I, right? And we also, another question we have is that when the split hits the bottom, and that is to say, how many levels are there in total in the tree? Okay, so let's look at these two questions. So when does expanding end? How many levels in total are there? And what is the per level summation? Okay, so looking at the problem again, we can notice that the subproblem, the size of the subproblem will decrease by a factor of 4, right? That is obvious. That is described by the recurrence itself. So when we do one split, the subproblem, the size of the subproblem will shrink by a factor of 4, right? That is factor of 4, and from here to here, it is also a factor of 4. And so we can summarize, we can basically conclude that the subproblem size for a node at depth I is n over 4 to the power of I. That is something obviously we can see, right? And so we can use this principle to know when the subproblem hits 1, right? Because eventually, when the subproblem hits 1, there's no way to further split it, right? So we can consider this as our base case, right? When the subproblem size hits 1, then according to this principle, we'll let n over 4 to the power of I to be 1. And then we will solve the value of I, okay? So I equals the logarithm with base 4 of n. So that means when I equals this value, the subproblem hits 1, right? So when I equals this value, we are at the bottom of the recursion tree. That's some useful piece of information, right? So in total, we will have that many levels, logarithm base 4 of n plus 1, okay? This plus 1 is outside the logarithm because the I starts from 0, right? For the level 0, I from I is 0, and for level 1, I is 1, right? And to the bottom level, I is the log 4 of n, right? So we have 0, 1 to log 4 of n, and that's log 4 of n plus 1 levels, okay? Yes, I'm answering John's question. We know that it's a logarithm of base 4. Right, that's purely from this inference. We know that the subproblem size at depth I can be described by this quantity, okay? And if this quantity hits 1, that is the bottom level, okay? So we know that when I equals logarithm base 4 of n, this quantity will hit 1. And Devin asks, why is it c times n over 4? Square. Yes, I think Tyler asks that question, yeah. Because we substitute n over 4 into the original recurrence, right? The original recurrence says that t of n equals 3 times t of n over 4 plus c times n squared, right? So we need to substitute n over 4 into that equation. Okay. All right, so that's the first part of useful information. And yeah, I will mention master theorem later because that would be a general solution to a problem like this form, to a recurrence like this form. Yeah. So we now look at the per level cost, okay? And we will need to use the fact that each level has 3 times, let me correct this typo here, 3 times more nodes. Okay. Share the screen. Okay. So each level has 3 times more nodes than the level above, than the previous level. Okay, so we're gonna use this fact. Okay, so the number of nodes, we have the idea that the number of nodes at depth I is 3 to the power of I. For example, for the first level, it is depth 0, I is 0. So in the root node only has 1 node. And for the level below I equals 1, we have 3 nodes. Okay, so the number of nodes at the depth I is this quantity, 3 to the power of I. Okay, and also the subproblem size is reduced by a factor of 4. That's what we already know. Okay, so the cost for each node at level I is this one, C times n over 4 to the power of I and raised to the power of 2. Okay, so this is a principle that holds to each node of each level. Okay, so then we simply multiply these two quantities together. The total cost for depth I is 3 times I times C times n over 4 to the power of I n squared. So that is this quantity, the product of these two quantities is the total summation for depth I or level I, okay, which simplified to this form, 3 over 16 to the power of I times C times n squared. Okay, so our guess in 2 slides ago was correct, actually. Okay, so it is pretty much a geometric series, right? And we're glad to see that, because in terms of a geometric series, it's easy to compute, to calculate the summation. Yes, each split will result in 3 nodes because the 3 in front of the t in the original equation, that's correct. The number of nodes will increase by a factor of 3 whenever we do the split. All right, so let's carry on to the next step. We're almost there, okay? So now we collect all the facts, put all the facts together. The bottom level is in that depth. The depth I equals logarithm base 4 of n, okay? And the number of leaf nodes in that, in the bottom level is 3 to the power of I, and we let I to be this value, right? So we got 3 to the power of logarithm 4 of n, and we switch the 3 and n, okay? And we've got the total number of leaf nodes at the bottom of the tree is n to the power of logarithm base 4 of 3. Okay, so I'm gonna continue with the the slide here, and we'll probably can able to answer your question later on. Okay. All right, so that's the bottom level cost, because bottom level is a bit special, and we know that the cost for the bottom level for the smallest case can be described by capital T of 1, and it is usually a constant time. Okay, so in a slides ago, when we introduce the question, we don't explicitly say that the cost for the leaf node, that is the cost for the smallest case, is constant, but that is usually the case. And we typically would say that at the beginning of the question. Okay, so now we assume that the cost for the smallest case is constant. So we have that many nodes in the bottom level, and we simply use that number times the cost T of 1, which is basically results in this big theta of n raised to the power of something. Okay, and that something is computed by the logarithm with base 4 of 3. Okay, and this is a polynomial function. Okay, and the efficiency is quite good. It is slower than a linear function, right? Because this quantity is less than 1. Okay, so now we've basically got everything we need to know in order to obtain the total cost. That is the summation for all the nodes in the tree. Okay, so we list all the nodes here, and for each level, we know that the summation can be described by a geometric series. Okay, so for any level I between the root node and the leaf node. So as long as I doesn't hit the bottom level, we can describe the total sum by this quantity. And when it hits the leaf node level, it should be described by this quantity. That is the bottom level. Okay, and that said, we're able to compute the total cost by summing up this geometric series from c times n squared to 3 over 16 times times c n squared plus 3 over 16 to the power of 2 raised to the power of 2, blah blah blah, blah until this level. Okay, so this is the last level before we hit the bottom level. Okay, because when we hit the bottom level, the I would be the logarithm with base 4 of n. That's where we hit the bottom level. So one level above, it is logarithm with base 4 of n minus 1. Okay, so that's basically we decompose the total cost for this recurrence into 2 parts. So part 1 is a summation of a geometric series, and the second part is the bottom level. It is the cost for solving all the smallest cases, to solving all the smallest subproblems. And the total would be the part 1 plus part 2. Okay, so we now need simply use some mathematical knowledge about the geometric series in computing the the total summation, right? So a geometric series, the summation of it can be described by the formula here. Oops. By the formula here, okay? Because we know I ranges from 0 to this quantity, and we just follow the formula, and we can obtain the summation for this geometric series, okay? And this term, we know that it has a limit value. It has when n is very big, basically this one the item here will disappear. Okay, so now we have the analytical solution for T of n, right? The solution looks like this way. And now we just need to consider the upper bound of it. Okay, So we need to utilize the property of geometric series, okay? Because our summation is always bounded by the infinity value of the geometric series, right? Because our inputs can not be infinitely long, okay? So let's just compute the infinity of this summation here, okay? And when the exponential term approaches infinity, this one becomes 0. And with some simplification, we know that the T of n is bounded by this function, okay? Which is a quadratic function plus basically a lower order polynomial function, okay? And therefore, we ignore the lower order term and claim that the upper bound for the original solution here, for the original recurrence, the running time, is bounded by n squared. That is a general quadratic function, okay? So here is an interesting step, right, that we want to compare. We basically compare the summation of a geometric series and a polynomial function. And the order of the polynomial function, right, is the logarithm with base 4 and 3. And actually, the 4 and 3 here are also from the original recurrence, right? So 4 is the speed of how we shrink the size of the subproblems. When we split the subproblem, it shrinks by the factor of 4. And 3 is the number of subproblems each time we do the split, right? So this quantity is determined by the form of the recurrence itself. So everything is determined once the recurrence is written, is fixed, okay? Alrighty. So that is kind of the basis for the master's theorem that we're gonna introduce in the next part. Let me see if I can answer John's question here. How does our big theta n squared factor into the amount of levels, given that so far we've focused on? So the big theta of n squared in the original recurrence is something we treated with a simplified way. We first remove the big theta and replace it with c times n squared, okay? So this c times n squared actually represents the cost related to the big theta of n squared in the original recurrence, because the original recurrence says T of n equals 3 times T of n over 4, right? Plus some theta of n squared, right? That's what we have in the original form. And this big theta cost actually exists. It exists in the form of this term, finally, okay? And this is the cost related to the splits and the combining steps, okay? While this term, this lower order term, is basically the cost of solving all the smallest subproblems, okay? So we are not ignoring any terms in the original recurrence at all. So it basically conserves all the information. And we use geometric series to summarize the total cost of all the combining and splitting steps. Okay, so let's move on to the next slide, okay? Alrighty. So that is the recursion tree method done. And the goal of the recursion tree method is to help us come up with a guess of the solution. So technically, the big O of n squared is still a guess because we obtain it from drawing some trees. So strictly speaking, we still need to use substitution method to prove that the big O of n squared is a upper bound of the original recurrence. Okay, so in order to prove that, we need to follow the definition. We need to find some constant d, right? We use d because we don't want to mess around with the c that we already use, right? We already use c here, so we want to use a different constants. Okay, we want to show that the t of n is bounded by d times n squared for n's that are sufficiently big. Okay, so that just to follow the rules of the substitution method. Okay, so substitution method basically needs to let me point here, needs to substitute this one, the n over 4, into the form like this, into the form on the right, which is the quadratic function here. Okay, so we substitute this this t of n over 4 with d times n over 4 squared. Okay, and we want it to be bounded. We want the whole thing to be bounded by d times n squared. Okay, so in order to making this inequality holds, we must have d should be greater than 16 over 13 times c, right? That's the d we want to find. Okay, so here's some review of the substitution method, right? What we want to claim, we want to stress is that the recursion tree helps you to get some guess, and then still we need to use this guess to strictly prove that this is actually true using substitution method. Okay, so this is the first step of mathematical induction is done. Okay, and what's left is to find the boundary condition and to find the proper n zeros. Okay, so which I'm not going to show here. Is it 16 over 3? No, because we want this inequality to hold, right? We will need to move the 3 over 16 to the right here, and which will result in 13 over 16 d times n squared should be greater than c times n squared, right? So eliminate n squared, so d should be greater than 16 over 13. Okay. So let's look at a more interesting example. Okay. Oh, where did the 13 over 16? No, because it is the results of moving this term to the right side. Okay, because the last inequality here says 3 over 16 times d times n squared plus c times n squared should be smaller than or equal to d times n squared. Okay, so we move this to the right, so which results in n squared should be smaller than 16 over 16 minus 3 over 16, right? times d times n squared, right? That's where the 13 is from. Okay. Alrighty. So in this example, we'll see that the recursion tree method is a very powerful tool. Even if the tree is unbalanced, okay? So we have a very irregular kind of recurrence. Say we have a recurrence like this. So what this recurrence says that when we do the splits from the original problem into smaller ones, we don't do the even split, but we do a proportional split. We solve the first 1/3 of the original problem, and then solve the first 2/3 of the original problem. So that's what this recurrence indicates. Okay, and with this recurrence, we are still able to draw some tree-like structure, right? We put the function c of n over the root node, and this is the left half, the right half, the left branch and right branch. And then we do the split to each branch respectively. And to the left branch, we need to substitute n over 3 into the original recurrence, which results in c times n over 3 as the node here, and n over 9 to the left branch, and the 2 times n over 9 to the right branch. And the values on the right is different because the value here is 2 times n over 3. So the node here with c times n over 2 times n over 3. And the values here is also kind of different. This one will be 2 times n over 9, and this one will be 4 times n over 9. That's the results of substituting these values into the recurrence. Okay, and we can do the further splits. And as you may already notice that our the values in each level is not evenly distributed. They are not even distributions. So that means some subproblems, some branches will reach the smallest case first, right? While some other branches on the right will hit the smallest how is that Cn splits into two values? Because that's the that's decided by the recurrence. The recurrence says that T of n has 3 components, which is, let me write it in another color. That is our first component. That is our second component and third component. We place them into a tree-like structure, right? We place the 2 over here, the n over here, the 1 over here, and the 3 over here. Okay, so the principle is that we always put the function related to the splits and combining into onto the root position. Okay, and we put that function in the node above, and we can place the costs for the sub-problems into the children node position. That's the general principle of doing this drawing these recursion trees, okay? Because we have capital T's here. The capital T's means that these are the time for solving the sub-problems. So the cost of the sub-problems go to the next level. Okay, so now let's consider the per level sum. We gotta do the same thing to have an idea of what the total cost could be. Okay, And we notice that, interestingly, in this particular case, the sum for the first level is C times n, and it also C times n for the next level, and actually for all levels, okay? So although the split goes uneven, but it seems that the cost for each level, the summation for each level seems to be even, to be same values, okay? And the branches grow in different speed means that if you observe the rightmost branch here, if you look at this branch, it decreases from C times n to 8/27, right? And for comparison, we look at this one, the leftmost branch. The sizes drops, the values in the node drops much quicker than this one, right? So that means the tree would be, some nodes will hit the smallest case earlier than others. So the left one will be, will first reach the smallest case, okay? And for comparison, so for estimation, we use the longest path from the root to a leaf, which is in this rectangle. On the right side, this is the longest path, okay? And we know that the node, the values in the node decreases by a factor of 2/3, right? And we use this as a estimation. So when this value hits 1, that's where we hit the bottom level, right? So when this value hits 1, I is the logarithm of 3/2 of n. So that is the depth at which the rightmost branch hits 1, hits the smallest case, okay? So, and we use this as an estimation, right? So if it is a binary tree, say if it is balanced, that means all the leaves, all the branches, they decrease at the same speed, and all the values in the nodes they are evenly distributed. Then the total cost could be the number of levels times the per level cost, C times n. So this is still a guess. The one I noted, indicated with triangle is still a guess, but we can use it as a sort of a guess, right? So if this is the case, then we can use n times logarithm of n to describe the total summation, okay? So we need to proceed a bit quicker for these points, okay? So it helps us to get obtain a guess, which could be big O of n times logarithm of n, okay? And but this is not a binary tree, right? It must have fewer nodes than that many leaf nodes, because many of the internal nodes are absent, because when this one, this one hits 1, these smaller values, they are already gone. They are already 0. They won't exist in this level, right? So the per level summation is not necessarily C times n. So this one is our approximation. So in theory, this is not necessarily true, but we can use it to come up with a guess, okay? And we will see that this guess could help us to get the correct solution to the original problem. If we assume that this guess is a good guess, we can use substitution method to show that the recurrence is actually bounded by this function bounded by n times logarithm of n. Okay, and we'll quickly show the first step of this substitution method. Right, we substitute n over 3 into this form, right? And 2 times n over 3, 2 times n over 3 also into this form. That's where we get this step. Yes, that is basically true. We use the recursion tree to obtain a guess. And then we simplify the terms over here. We will get something like this. So all the coefficients here are constants. Okay. So in order to making this inequality hold, because we want the upper bound, we want this upper bound to hold, we want the whole thing to be smaller than d times n times logarithm of n, we must satisfy that d should be, we must satisfy that this quantity should be greater than c, right? Because there's a negative here. We want the whole thing to be smaller than this term, right? So we can solve d by such a inequality. Okay, so that is the first step of the substitution method. But we see some good sign, right? We can find the d that helps starts the first step of the mathematical induction. Okay, and we will, if you do the complete steps for the mathematical induction, we will see that it is true. The big O of n times logarithm of n is actually a valid upper bound for the original recurrence. Okay. All right. I would like to recap a little bit and start the next topic. So to draw a recursion tree is very helpful to devise a guess to the solution. And in the extreme cases, the tree does not have to be a complete tree. It can be the tree like the one we just did, right? But we can use some estimation, you use some approximated values to get some guess of the out of the tree. All right, now let's enter the last parts, master method. Probably we don't have sufficient time to fully cover it because I need to leave earlier than 3:15. And but I'm gonna go through all the cases that are necessary to help with all the assignment questions. And we will cover the rest parts of master theorem and another example in next Tuesday's class. Okay, so we'll get started with master theorem here. All right, so based on the trees we have drawn, this is the recurrence that we use to draw the first tree in the previous slides, right? The solution is two parts. It is the first part is a summation of a geometric series, right? And the second part is the summation at the bottom level of the tree, okay? So I wrote these two as in bold because they are kind of related, okay? So this relationship basically indicates that the cost of the root node dominates the total cost, right? The c times n squared is the value of the node, of the root node. Okay? And the solution is also dominated by that function in the root node, okay? So what if then the root node costs less? What if the root node is a linear function or even constant? Then this node, this part in the solution should also change, right? And if this is a constant, then compared to a constant, this one becomes a higher order term, right? And if that is the case, then the upper bound should be determined by the big theta of n to the power of something, right? So I'm showing that the relative growing speed of the two components can decide the final solution to the recurrence. Okay, so we can imagine that the solution would be changed if the root node changes its form. Okay, all right. Let's look at the full the outline of the master theorem, how it looks like. Okay, it's basically a cookbook for solving recurrences of such a form. It does not solve recurrences in all forms. It doesn't solve all kinds of recurrences. It only solves recurrences in this form. We need to, in this recurrence, we split the original problem into A subproblems. The number of subproblems is A, and the size of the subproblem is n over b. Okay, we have two constants. And also, there is a function related, f of n, which defines the cost of splitting and combining. Okay, and a and b are greater than 1. They are constants. And f of n is a asymptotically positive function. It means it's eventually it is a positive function. It is and doesn't have negative values. Okay, so this recurrence means that we divide a problem of size n into A subproblems, and each subproblem has a size of n over b. Okay, and the f of n is the cost of dividing and combining. Okay, so this is what the master theorem says. The T of n has the following asymptotic bounds. We have 3 conditions. The first condition says if f of n has this one as its upper bound, the n to the power of logarithm with base b of a minus some epsilon for some constant epsilon that's greater than 0, then the T of n is bounded by the big theta of this polynomial term. Okay, so we have a if and then condition. So if f of n is bounded by this polynomial term, basically, then the T of n is also bounded by this polynomial term. That's what this condition 1 says. The second condition says if f of n has a tight bound, or f of n has a tight bound of this polynomial term. In another way, f of n grows as fast as this polynomial function, then T of n is bounded by this polynomial term times the logarithm of n. That's the second condition. The third condition is a bit longer, but as you may guess, it says if f of n is the upper bound for the polynomial term, or this polynomial term is the lower bound for f of n for some epsilon, and if this regularity condition is satisfied, okay, so this basically says that the total cost of solving all the subproblems should be bounded by some constant c, and this c is smaller than 1. Okay, so it basically says that solving all the subproblems should be not solving all the subproblems, but the cost related to the dividing and the combining cost related to all the subproblems should be smaller than the same cost of the original problem, okay? So as long as these conditions satisfied, T of n should be bounded by f of n. Okay, so that's 3 conditions for master theorem. Okay, so these 3 conditions here, they are kind of very rigidly, strictly defined, but we can understand it from a more intuitive point of view. So it basically says that we are comparing 2 functions, the function f of n and the function, the polynomial function n raised to the power of logarithm b of a. And in case 1, the logarithm term is larger, okay, or it is the higher upper bound. Then the final solution is bounded by the logarithm term, by the polynomial term. And in case 3, the function f of n is larger or is higher. Then the solution is bounded by the function f of n. And in case 2, the case 2 says that the 2 functions, they are of the same speed. Okay, so they are bounded, they are tightly bound for each other. And we simply multiply the polynomial term with a logarithm term, and that is the bound for the final solution. So this is some intuitive idea of what the master theorem says. Okay. So the technicalities, I think I'm gonna skip through it. I'm gonna talk about this next Tuesday, and I would like to use a example to showcase how we can use master theorem. Once we know the rules, it's quite easy to understand. Okay, so in this maximum sub-array problem, we have a equals 2 and b equals 2. Right, and we have that the logarithm of base 2 of 2 is 1. So the polynomial function is a linear function, right? And also the f of n is also a linear function. So that means we need to use the case 2. The f of n and the polynomial, they grow at the same speed. So it's case 2 we must apply. So we can directly come up with a solution that's the T of n is big theta of n times logarithm of n. Okay. And some other examples we can consider, but this example involves some technicality issue with master theorem. So I'm gonna skip it. So this one could be a good choice. So in this case, the recurrence in this form, a equals 9, b equals 3. So the logarithm of b with base b of a is a quadratic function. And the quadratic function grows faster than the f of n here. F of n here is a linear function. So we can use case 1. So the final solution is bounded by the quadratic function. So that is the master theorem quite briefly, and we're gonna revisit that in the next week's class. And I'm going to answer the question. So Scott, I think you can have your question here now.
All right, thank you. I just had a question about substitution from the last lecture.
Yes.
It had to do with when they were comparing 4, like 4 was less than c times n log n.
Mm-hmm.
And it said that when c is greater than or equal to 2, and I think they were plugging 2 in for n at that point, and it said like 4 is less than or equal to like 1 point something, and they said it was true.
Let me go to the slide quickly. need to share my screen again.
I think it was that one.
This one, yeah.
Yeah, where it's t of 2 equals 4,
Mm-hmm.
Which is less than or equal to c times 2 times log 2.
Mm-hmm.
But if you plug in 2 for c, it's not true, right?
Wouldn't it be equal in that instance? Because if we're plugging in 2, then we have 2 times 2 is 4. Log, we're to assume it's base. Would we assume that log is base 2 or base 10? Because the base isn't written. If it's base
That's
2,
base 2. That's base
if
2 that
it's
we are
base
assuming.
2, then it would be equal then.
Oh, that makes sense. I thought it was base 10.
Yeah, that's base 2.
Okay, thank you.
Yeah.
And then the next one's like base 3, right?
Actually, base 2.
Base 2? Okay.
Yeah, base 2. But the results of C solving like this one, we should use our calculator to see roughly how C is, because we don't know the exact value of logarithm of 3.
Okay.
Yeah, but we'll choose the bigger value, the bigger one, the bigger solution for C by solving this blue inequality and the red inequality respectively.
Okay, thanks.
Yeah. I've got another question. Yeah, should be the same as the number of the subproblems.
So I can make sure that I've got the timing right for due dates. Our homework 1 is due next Thursday. Or next Friday, sorry.
Next Friday, yes, next Friday.
Okay, thank you.
Yes. Yeah, I'm going to schedule a new time for office hours. So I'm thinking about either Monday afternoon and Thursday morning, or Tuesday afternoon and no, Tuesday. I don't have time for Tuesday, or Wednesday afternoon and Tuesday morning. So I'm gonna send out emails about this. So yeah, it's gonna be a bit messy, but I hope I will try to have office hour for as many people can come, so as less conflict for you guys as possible. The size of subproblems, so it was log base of 2. So I'm not sure, David, which one you are talking about.
Hi, sorry, I have a different definition of the master theorem from a different class, so I don't have a proof for that. I'm looking at a different way to do it.
The size of subproblems, so n equals 2 use log base 2. That's true, I think, because in that case, the size of subproblem is n over b, and b is 2. So the base should be 2. But yeah, so I think Robert is correct. LG is for base 2. And for any logarithm function in the master theorem here, I think I specify the base explicitly. Yeah. But for in general, for the general growth of function speed, when we talk about a logarithm function, the base doesn't really matter a lot, because all logarithm functions, they are at the same, they have the same asymptotic property. They all grow slower than polynomial functions, no matter what the base it takes. So, all right, guys, I gotta go today, and thank you for coming to the first live lecture. I think it's quite good discussion going on here, and I will upload the video later to Canvas, and also there will be some quiz questions which will be due on Sunday. And hope you have a good day. Bye bye, guys.